Hi everyone, Dr. P here, and in this video we're going to take a look at nomenclature, naming chemical compounds. And so what we're going to look at is a systematic way of naming things. And this is different than, say, common names for things. So for example, table salt is a common name, but sodium chloride is a systematic or IUPAC name. IUPAC is the International Union of Pure and Applied Chemistry. All right, so let's look at some rules for naming. And I'm going to break things down maybe a little differently or have slightly different terminology than the text does. But let's look at first binary ionic compounds. And we'll call some of these binary compounds. We'll see there are different types, but these will be type 1 binary. So binary is a cation plus an anion, or cations plus anions. So for our binary ionic compounds, we want to name the cation first, then the anion. If a cation is just one atom, so monoatomic, so monoatomic cations, monoatomic cation gets name from element. So for example, Na plus is simply sodium, and then a monoatomic anion also gets its name from the element. Plus the suffix ide, I-D-E. So for example, Cl minus is chloride. So in this example, if you are faced with NaCl, that becomes sodium chloride. Okay. Now you want you want to, for ionic compounds, you don't need to pay attention at this stage for these type 1 compounds to how many of a particular atom there are or element there are. What do I mean by that? Well, let's look at some more examples. MgBr2. Why do I have the 2 there? Well, Mg always forms a 2 plus ion, and Br always forms a minus ion. So in order to make a compound, we have to get them to match up. Okay, and the name of this is simply magnesium bromide. All right, and there's a figure here. So I'm just going to say see figure 2.29 for common ion charges. And let's take a look at this figure here. All right, so let me zoom in a little bit. So we can see here that magnesium forms a 2+ ion. And I talked about this in the last video. It does that because it likes to give up 2 electrons. So then it would have the same number of electrons. So if I give up 1 and then 2, same number of electrons as the noble gas neon. Bromine likes to pick up 1 electron so it can look like krypton. So if I have Br- and Mg2+, I need 2 bromines. So my 2- equals my 2+. Okay, our compounds are always going to be net neutral. So our anion total charge has to equal our cation total charge. But I just call it magnesium bromide. Let's do, let's see here. Let's do Ca3P2. This is calcium phosphide. Now, how do I know that? Well, it's calcium, Ca, and then P is phosphorus, so phosphide. I don't have to worry about the 3 or the 2. Now, why do I have the 3 and the 2 there? Well, calcium is 2+. Phosphide is 3-. So I need 3 calciums to make a total of 6+, and 2 phosphides to make a total of 6-, and then those cancel out and we have a neutral compound. Okay, so those are the type 1 binary atomic compounds. And they involve things where you only have 1 possible charge. So notice in this table, all of my anions here, and then my cations in groups 1 and 2, and some of my cations in the middle. These are what we call transition metals in the middle here. Some of them, like nickel, zinc, silver, they only form 1 possible ion, but some can be a little tricky. Like copper could be 2+ or plus. We don't know necessarily what it's going to be. So we need to have a different way of naming things. And that's where we get into the type 2 binary ionic compounds. Let me zoom out here. I forgot I needed to zoom out. So these ones feature a cation that has multiple oxidation states. That is, it can have different possible charges. Okay, an example of this is Fe2+ versus Fe3+. So iron 2+ versus iron 3+. So in this case, the charge on the metal must be specified. And to do this, we use Roman numerals. So, for example, FeCl2 is iron 2 chloride. FeCl3 is iron 3 chloride. Whoops, sorry about that. The Roman numeral refers to the charge on the metal. So here I have Fe2 plus, and then I have 2 Cl minus ions, so that adds up to neutral. Here I have Fe3 plus and 3 Cl minus, so that adds up to neutral. And again, the Roman numeral tells me the charge on the metal. It doesn't tell me how many metal ions. It doesn't tell me how many anions we have. It only tells us the charge on the metal. Some other examples here. Since we're doing iron, Fe2O3. What would that be? Well, that would be iron something oxide. Okay, iron and oxide. Now, oxygen is usually 2 minus. And if I have 3 of them, that gives me 6 minus total on this side. So I have to have 6 minus for my iron, and if I have 2 irons, that means I've got, sorry, not 6 minus, 6 plus. If I have 2 irons, that means I have to have Fe3 plus. So this would be iron 3 oxide. Okay, and now something like this you definitely want to practice. Now I do want to mention there is an older system as well. And in this older system, the species that had the higher charge would get the suffix "ic," and the species with the lower charge would get the suffix "us." So, thus we have FeCl3 becomes ferric chloride, and FeCl2 is ferrous chloride. All right, so using the Latin term for iron here, so that's where we get Fe from ferrum. So if it was chromium, we would have the chromic cation would be Cr6 plus, and the chromous cation would be Cr3 plus. For copper, because it's Cu cupro, it would be cupric and cuprous, etc. So that's an older system, and I just want to mention it. We're going to avoid using it, but you might run across it. All right. Now, another thing that you may need to be on the lookout for is some ionic compounds with polyatomic ions. And you should take a look at table 2.5 for you should take a look at table 2.5 for some examples of polyatomic ions. So let me bring in table 2.5 here. So we have ammonium, NH4 plus, hydronium, which tends not to form compounds, peroxide O2 with a total 2 minus versus oxide, which is just O with a 2 minus, hydroxide OH with a minus charge, cyanide CN with a minus charge, carbonate CO3 with a 2 minus charge, and this charge applies to the overall whole thing. So you could think of the CO3 as a carbon and 3 oxygens bonded together somehow, and it'll be a covalent bond. And then that overall group has that charge of 2 minus. So it acts like a, if I want to, I could go ahead and put in some parentheses here just to show that 2 minus applies to the whole overall group. Table 2.5 continues on the next page. We've got all sorts of things: bicarbonate, nitrate, nitrite, sulfate, sulfite, etc. And some of these correspond to acids as well, and we'll talk about acid nomenclature in just a little bit. All right. Oh, there's one more oxyanion. Yeah. One more thing with the anions, some of these polyatomic anions, the oxyanions. So perchlorate, chlorate, chlorite, hypochlorite. Notice the trend here in the number of oxygens. Chlorate has the most, has 3 oxygens. Perchlorate has the most, 4 oxygens. Chlorite has 1 less, 2 oxygens. Hypochlorite has 1 less, just 1 oxygen. So it's kind of similar to things such as sulfate has more oxygens than sulfite. So make sure that you are on the lookout for your oxyanions. So let me just kind of add that in here. We'll say oxyanion suffixes. So we'll say prefixes and suffixes. If we have hypo as a prefix and ite as a suffix, that's our fewest oxygens. And then our most oxygens down here would have per as the start and ate as the suffix. And in between we just have ate, and we also just have ite. So we have most oxygens as a prefix of per and a suffix of ate. So that ClO4 has 4 oxygens, that's the most, so it's perchlorate. ClO2, well, that's 4, 3, 2, chlorite. ClO, hypochlorite. BrO2 with a minus charge, that would be bromite, because it's from the bromine compound. SO4 versus SO3. SO4 is sulfate, SO3 is sulfite. There are only 2, so we use the ones that don't have the prefixes. We only need these when we have those halogen oxyanions. So yeah, it's a lot to kind of keep track of. Let me just wrap up with one, or actually two last bits. One is acids. Let's take a look at acids. And so acids are substances that produce H plus in solution. We'll look at some more definitions of acid later on. So what we need to do is, when we name those, we need to look at the name of the anion. I'm just saying, let's just look at the anion. How about that? We'll worry about the name of the anion in just a minute. So if we have an anion without, W/O is without oxygen. We'll use a prefix of hydro and a suffix of ic and acid. So examples of this could be HCl, which is hydro, and Cl is our Cl minus is our anion, so hydrochloric acid. You know, I could have something like I don't know, H2 Se, for example, would be hydroselenic acid. But that's a metalloid, so it's getting into some, maybe we're getting into covalent territory. Not quite sure yet. All right, if we do have an anion with oxygen, and this is where it's important to know the names of your oxyanions. If the anion is 8, that gives us an ic acid, and if the anion is ite, that gives us an us acid. And then we use hypo and per prefixes as necessary. And so examples here could be HClO. Now if I cover up my H plus there, that's ClO minus, that was hypochlorite. So that becomes hypo, there should be an O there, hypo. This becomes hypochlorous acid. We could have, let's say, HiO4, and that's the per iodate ion, so that's per iodic acid. Yes, I know it looks like periodic acid, but sometimes chemists do put the emphasis on the wrong syllable. In fact, if you want to tell a chemist from a plumber, ask him or her to say the following word. So a chemist would typically say this word, pronounce it unionized, and say a plumber or someone else in the trades who may belong to a union would say unionized. Sort of like per iodic acid versus periodic acid. It's not periodic, it's per iodic. Anyway, so those are the rules for those are the rules for naming ionic compounds. I think I'll end this lecture because it's gone on for a little bit, and we'll record one more talking about naming covalent compounds, and then maybe also looking at coming up with structures given names. All right, so until then, stay safe out there, please. Bye now.